To video 3 of section 410, antiderivatives. This is Mrs. Allen, and just looking at example 4 from this lesson, that we found that we could find the function f if we worked backwards and then utilize the specific information for the function, the first derivative and the second derivative, to be able to write the specific function given that specific information. So we have f of x is equal to cosine x plus x squared plus x. So the next example that we're going to do is we're going to graph a function, capital F of x, and it says the graph of a function is given. Make a rough sketch of an antiderivative, capital F, such that, or given that, capital F of 0 is equal to 2. So what I'm going to do first is I'm going to say we want to graph, down here I'll put the letter here, we're going to graph capital F of x down below, but in order to graph an antiderivative, I start to think of lowercase f of x as if it is the derivative graph and I'm undoing the derivative to get the antiderivative. So the process is something like this. I would say, okay, y is equal to f of x is the antiderivative. And my guitar is in the way here, but I'm going to run over here. Okay, so is the antiderivative graph. So we do know that we have the point 0, 2 on the graph because we're told that we have f of 0, capital F of 0 is equal to 2 from the given information. So you notice that we have a point on the graph, and here it is, and that would be 0, 2. Okay, and this graph seems to exist with x greater than 0. Okay, so let's take a look at f of x. Now remember, if I'm looking for f of x, the antiderivative, I kind of treat the function lowercase f like it is the derivative. So I treat it like it's the derivative. Like it is the derivative graph. Okay, I know, and some of you are probably sitting there going, you know, I'm not really sure, Mrs. Allen, but you'll get it. Hold on just a second. Okay, so the third thing is I'm going to say, all right, where remember, I'm treating this like the slope graph, where f is negative, then that would mean, like, remember, that's the derivative, f, lowercase f, then the function, capital F, is decreasing. I'm going to abbreviate that, D-E-C-R period. And let's look at the intervals that occurs at. So lowercase f is negative here and here. So it looks like it's negative from 0 to 1. That's 0 to 1. And union with 3 to infinity. And there we go. So then I'm going to use a different color here for the upper portion. It looks like f is positive. F is positive if capital F is then increasing. And it looks like it's positive. F is positive on the interval then from 1 to 3. 1 to 3. Okay, so we've got that. Now, we know something when the slope is negative and then it becomes positive. We know then what happens. Remember, we're treating this like it's the slope graph, right? Like it's the derivative. So if I know the slope is negative and then it becomes positive, that means that I have a what? Looks like it's negative, goes to, think about it like this. Slope negative, slope positive. It looks like I have a minimum. So at this point, capital F has a rel or a local min. I'm just going to call it a min for now. Okay, right here. So then if you see that slope is positive at this changeover and slope becomes negative, then we'd be looking at this point where if you look at it, f is equal to 0 at this point. But here, f is negative, f goes positive. this is where capital F has a minimum. So at this case where F is also equal to 0 here, then that would mean that F would have a maximum. So we have an F maximum here, capital F, because you can see that the slope would be positive and then go to a negative slope, positive, then to a negative. You would have a little mountaintop experience there. Where you have a little valley experience over here, you have a minimum for the left-hand side. So let's put some of this in here that we know now that F of 1 is a minimum, and F of 1 is equal to F of 3 is equal to 0, and F of 3 is a maximum by the first derivative test. Okay, so we're going to put that in there. Okay, so let's look at number 5. Number 5, then we're looking at what's going on at the graph, what's happening as x is getting bigger. So we notice some things going on. It looks like for number 5, the information I put is that I'm kind of looking at what's happening to the function as x comes out here. What's happening? It looks like there might be a horizontal asymptote. I would kind of guess that F, that would look like capital F would get flatter. F has a horizontal asymptote. And that would then be, we would look at F getting flatter. The limit as x goes to infinity of f of x would equal 0. So that would say that f is flatter. Capital F of x is flatter because it has a slope of 0. So then I want to look at f double prime. Just getting all the information here. So let's notice f double prime. What is f double prime? So f double prime is equal to capital F prime. I'm sorry, capital F double prime is equal to f prime. So let's take a look at what we get here if we have f prime of 2 is equal to f prime of 4 is equal to 0. So let's address what f double prime is then. So if, and recall that if we have our function f of x here, we have a maximum and a minimum. So we can see at these 2 points at f prime of 2, we can see that that's equal to 0. And down here we can see that f prime of 4 is also equal to 0. And then if we look at that then, knowing that f prime, double prime is equal to f prime, capital F double prime is equal to lowercase f prime, then we have capital F double prime of 2 is equal to capital F double prime of 4. And they would be equal to 0 also. So that would tell me then, now remember you're looking at the sign of a derivative, so let's look at the number line clearly. So if we go from 2 to 4, that I would say, okay, what are the signs of f prime and f double prime? Because we know that they're equal. So if I look, I see that from 0 to 2, the slope is then going to be positive. So remember, we're talking about the slope of f, the graph of f, and I'll scroll up in a moment. and f prime is negative, the slope is negative between 2 and 4. So let's just look at this. So the slope is positive. Let me highlight that in positive pink. So if I look at the slope being positive here, and I'm already in yellow there, but the slope is also positive here on this endpoint. So in those two places, the slope is positive, but in the middle section, the slope is negative. So remember, the slope of f prime is equal to the second derivative of capital F. So then we can look and we can say, okay, that the slope is positive again at the end. So on the intervals, our slope goes from positive, negative to positive. So we know the information about the function f here is that when the second derivative is positive, then we know that f is concave up. We know that f is concave down when the second derivative is negative, and we know again that it's concave up. So we know information at 2 and 4. Since the slope is equal to 0 at both places, we know that we have a point of inflection, POI, at 2 and at 4, because there's a change. Not only is the slope equal to 0 at those points, there's a change in concavity. So let's take this information and see if we can't put it together to draw a graph. So we start at the point 0, 2, and we know that the function is decreasing on the interval from 0 to 1 and 3 to infinity. So I'm going to draw it so that when it's decreasing, remember we have a minimum at 1. So I'm going to go down just a little, and then we're just doing a reasonable kind of sketch. And then it's going to come up a little. And then at 2, I have a point of inflection. And then my function is decreasing from 0 to 1, increasing from 1 to 3. So even though you have a point of inflection, it's increasing until you get to 4. And here's 1, 2, 3. Sorry, until you get to 3. And then I know at 3, I have a maximum point. So I have a max at 3, as we said, and I have a minimum at 1. And then the function goes to 4 as, let's take it down like this. So at x is equal to 4, there's another turning of the graph, but the function is still, you have another point of inflection at x is equal to 4. But yet you continue to be decreasing. Let's look at the intervals of decrease. It's actually showing right up on here. So we've got the intervals of decrease right up here. So we have from 0 to 1, and then from 3 to infinity. So we want to accent that fact. But with a change in inflection, we know that it's going to be decreasing but concave up. And this will continue to level off, as I said, so that it looks like the slope becomes 0. So we have a min, we have a max, we have a min, we have a max, and we have 2 points of inflection as critical information on this graph. And then, of course, the limit as x goes to infinity, the graph looks to level off somewhat and looks something like that. Remember, this is a reasonable graph. It is not 100% accurate. We're just getting an overall idea of what happens. So here is the graph of our function, f lowercase f of x, and its possible antiderivative based on the information that we extrapolated. That's it for this video. We'll stop here and pick up the next video for 410 antiderivatives. And see you later.